somewhere in the dark between the stars, a small object turns in silence. It is only about 20 kilometers across, no wider than a quiet city, yet it holds more mass than our sun, packed so tightly that a single sugar cube of its matter would weigh as much as a mountain range. Around it, space itself seems to bend and hum, and, wrapped around its tiny body, is a magnetic field so strong that our minds cannot really picture it. This is a neutron star, and a rare kind of neutron star, called a magnetar, carries a field so fierce it may be the strongest in the known universe. To find one, imagine drifting slowly outward from Earth, past the pale blue curve of our own world, past the moon, past the calm rings of Saturn, out beyond the last cold planets. Keep going, cross the long silent gulf, where the sun becomes only another star. Move further into the soft glow of the Milky Way, where dust lanes curl like slow rivers of shadow. Somewhere in that river, a massive star died a very long time ago. What it left behind is what we are looking for tonight. The star did not simply fade. It collapsed. Its outer layers were flung into space in a burst of light, brighter than 1 billion suns, and its core, crushed inward by its own weight, became something the universe rarely makes. Protons and electrons were squeezed together until they turned into neutrons, a whole star folded into a sphere the size of a small island. One small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like, one waiting each evening. Subscribe and let it find you. We think we understand parts of what happened next. Gravity pulled the neutron core into an almost perfect ball. The old star's spin sped up, the way a skater pulls in her arms. And the magnetic field, once spread across a giant glowing body, was pressed into that tiny surface. The field grew stronger. In some cases, it grew unimaginably stronger. Why some neutron stars end up with modest fields, and others end up as magnetars with fields 1,000 times fiercer, is a question we cannot yet answer. There are theories. One idea suggests that if the collapsing core spins fast enough, a kind of internal churning acts like a dynamo, winding the field up to extreme strength. Another view is that the field was already unusually strong in the parent star, and the collapse simply concentrated what was there. Both ideas have supporters. Neither has been proven. The truth may be a mix of both, or something we have not yet imagined. What we can say is this: a Magnetar's magnetic field is estimated to be about 1,000,000,000 times stronger than Earth's. That is a 1 followed by 15 zeros. At such strength, the very rules of matter begin to shift. Atoms are thought to stretch into thin needles. Empty space itself may behave in strange ways, and if you could somehow approach one, the field would begin to unmake you long before you ever touched the surface. Yet from far away, a magnetar looks almost still, a dark, quiet marble against the deeper dark. Only now and then does it flare. In 2004, one such flare, from a magnetar roughly 50,000 light years from Earth, briefly disturbed the upper edge of our atmosphere, a whisper of energy crossing half the galaxy, still strong enough to be noticed here. What caused that flare deep inside the star remains an open question. Some researchers wonder if the crust cracked under magnetic strain. Others suspect a sudden shift in the tangled field lines below the surface. We are still guessing. Tonight we will sit with these small, dense, secretive stars. We will wander around them slowly. From the outside in, we will look at their crusts, their spins, their strange twin lights, and the puzzles buried under their iron shells. We will not solve the mystery. Nobody has. The heart of a magnetar is one of the least understood places in physics, but it is a beautiful place to think about as you rest. A calm, turning object far away, cloaked in forces we barely grasp. It has been there for thousands of years, maybe millions, quietly doing something no laboratory on Earth can copy. And somewhere out there, right now, one is turning, one is flickering, one is holding its breath before the next slow flare. Let us drift toward it together, in no particular hurry, and see what we can gently learn. Let us start with the simplest picture. A neutron star is what remains when a giant star runs out of fuel and collapses inward on itself. The outer layers blow away in a bright explosion. The core, crushed by its own gravity, falls into something small, dense, and strange. What settles at the center is only about 12 to 15 miles across. That is smaller than most cities you have ever driven through. Yet inside that small ball sits more mass than our entire sun. Sometimes twice as much. Imagine taking something 1/3 of a million times heavier than Earth and squeezing it down until it could fit inside the boundary of a quiet town. The result is a kind of matter that does not exist anywhere else we can reach. To picture the density, try this. Scoop up a single teaspoon of neutron star material. That 1 teaspoon would weigh about 1 billion tons on Earth. 1 billion tons is roughly the mass of every human being alive today, all packed into the tip of a small metal spoon. It would sink through the ground, through the crust, through anything you tried to hold it with. On Earth, such a spoonful cannot exist. The pressures needed to hold it together only appear in the crushed heart of a dead star. The surface itself is thought to be smooth, in ways we cannot fully imagine. Any mountain on a neutron star would rise no higher than a few centimeters. Gravity there is so strong that the tallest hill would be about the height of a coin lying on its edge. If you could stand on that surface, though of course you could not, your body would flatten into a thin film in less than a heartbeat. Gravity at the surface is roughly 200 billion times stronger than gravity here on Earth. Now consider distance. Neutron stars are scattered throughout our galaxy, and the closest known ones sit hundreds of light years away. A light year is the distance light travels in a year, moving at about 186,000 miles every second. So even the nearest neutron star lies a distance that light itself needs centuries to cross. The Magnetars we will spend most of these hours wondering about are usually farther still, tucked into corners of the galaxy thousands or tens of thousands of light years from here. Their ages vary. Some neutron stars are old, spinning quietly for hundreds of millions of years, cooling slowly in the dark. Others are young, only a few thousand years past the explosion that made them. Magnetars tend to be the young ones, no more than about 10,000 years old in most cases. That is a blink in the life of the galaxy, and it is one of the puzzles about them. If Magnetars are always young, does that mean their strange behavior fades as they age, or does something else happen to them that we have not yet learned to see? The composition is where the picture grows softest at the edges. The outer crust is thought to be a thin shell of iron and other heavy elements, crushed into a lattice harder than any metal we can make. Below that, protons and electrons squeeze together until they merge into neutrons, giving the star its name. Deeper still, no one is quite sure what waits. There may be a strange soup of free quarks, the tiny pieces that normally live locked inside protons. There may be something we have not yet named. The interior is one of the great open questions in physics, and we will return to it many times tonight. The spin is another wonder. A young neutron star can turn hundreds of times each second. Older ones slow down, taking seconds or minutes for a full rotation. Magnetars sit somewhere in between, usually spinning once every few seconds, which sounds slow until you remember that a whole sun-mass city is completing a full turn in the time it takes you to breathe out. And then, wrapped around all of this, is the magnetic field. Even an ordinary neutron star carries a field 1,000,000,000,000 times stronger than Earth's. A magnetar carries one 1,000 times stronger still. Where that field comes from, how it forms so quickly, and why only some neutron stars grow such fierce ones, we do not yet know. There are theories, and we will sit with them in the coming hours. For now, hold the picture in your mind: a city-sized ball, heavier than the sun, spinning in the dark, wrapped in a magnetic force we cannot recreate anywhere on Earth. That is the object at the center of tonight's long, quiet question. To understand where a magnetar comes from, we have to go back to a moment of stillness before the storm. Somewhere in a quiet corner of a galaxy, a massive star has been burning for millions of years. It is many times the size of our sun, blue-white, hot enough to shine across whole spiral arms. Deep inside it, layer upon layer of nuclear fusion has been steadily building heavier elements from lighter ones. Hydrogen fuses into helium, helium fuses into carbon, carbon into oxygen, then neon, then silicon. Each new layer nests inside the last, like the skins of an onion made of fire. At the very center, something quiet and final is forming: iron. Iron is the point where fusion stops paying its bills. Fusing lighter elements releases energy, and that outward push holds the star up against its own weight. But iron does not release energy when it fuses. It takes energy in, so as the core fills with iron, the star loses the one thing that has kept it standing for eons. The furnace at its heart begins to fail for a while. Gravity and pressure hold their standoff. Then, in less than a second, everything breaks. The iron core, which may be about the size of the Earth, but far heavier, collapses inward at nearly a quarter of the speed of light. What was a ball of dense metal becomes something entirely different in the blink of an eye. The atoms themselves cannot survive. Under that crushing weight, electrons are shoved into protons, and the two combine into neutrons. The empty spaces inside atoms, which normally make up almost all of their volume, vanish. Matter becomes something far more compact, far stranger, a sea of neutrons. The collapse only stops when the neutrons themselves refuse to be pushed any closer together. A kind of quantum pressure called neutron degeneracy pressure finally pushes back. In that instant, the falling outer layers of the star slam into the newly formed core and rebound. A shock wave, helped along by a flood of tiny particles called neutrinos, races back outward. The star tears itself apart in a supernova, one of the brightest events the universe ever produces. For a few weeks, a single dying star can outshine an entire galaxy of hundreds of billions of stars. Left behind in the wreckage is the newborn neutron star. It is roughly the size of a small city, but it contains more mass than our sun. Its surface temperature may start near 1,000,000,000,000 degrees. It spins many times a second, sometimes hundreds of times a second, because the collapse concentrated the old star's rotation into a much smaller object, the way a spinning skater pulls in her arms and spins faster. Most neutron stars settle into a fairly ordinary life after this violent birth. They cool, slowly, spin down slowly, and shine as pulsars for millions of years. But a small fraction of them do something else. They become magnetars, wrapped in magnetic fields trillions of times stronger than any we know on Earth. How this happens remains one of the open questions in the science of these objects. One idea is that if the collapsing core was already spinning very quickly, a churning motion inside the newborn star could act like a giant dynamo, winding weak magnetic seed fields into monstrous ones. In this picture, only stars that collapse with just the right spin become magnetars. That would explain why they are so rare. Another idea is that the strong magnetic field is not born fresh at all. It might be inherited, passed down from the original star, whose own field was concentrated as its core shrank to a tiny fraction of its former size. In that view, the magnetar's power is a memory of the star it used to be. Both ideas have supporters, and both have problems. The dynamo theory needs very specific spin rates that not every progenitor star seems to have. The inheritance theory struggles to explain fields quite as strong as the ones we observe. It is possible that both processes play a role, or that some third process, still unnamed, is doing most of the work. The evidence remains incomplete. What is clear is that the ingredients for a magnetar are extreme even by cosmic standards. A star must be born massive. It must burn through its fuel in a certain way. It must collapse under just the right conditions of spin and pressure. And then, when the dust of the supernova finally drifts away, what is left behind is a small, dense, deeply magnetized object whose interior we cannot yet see into, and whose true nature we are only beginning to imagine. To understand what a magnetar is, we have to think about what a magnet really is. On Earth, a magnet is a piece of iron with its atoms lined up in the same direction. Each atom acts like a tiny compass needle. When enough of them point the same way, they pull on other iron objects across a small stretch of air. A refrigerator magnet holds a note in place. A hospital scanner uses a magnet strong enough to lift a car. Both feel powerful in their own way. Both are still whisper quiet compared to what a magnetar carries in its skin. A neutron star is not made of iron, at least not mostly. Its outer crust holds a thin shell of familiar elements, packed so tightly that the atoms lose their soft, cloudy shape. Below that, the matter changes. Protons and electrons squeeze together and merge into neutrons. A neutron has no electric charge, yet somehow, in a magnetar, this quiet sea of neutrons and thin currents of charged particles produces a field trillions of times stronger than any magnet ever built by human hands. How that field forms and how it lasts is still a mystery we have not fully solved. One idea is that the field is a memory. The parent star, before it collapsed, held its own gentle magnetism spread across a body larger than the sun. When the core fell inward, the field lines were pulled with it, packed into a ball only 12 miles wide. Squeezing a field into a smaller space makes it stronger. Some researchers believe this squeezing alone can account for what we see. Others are not convinced. The numbers, when you run them, seem to fall short of the fiercest magnetars by a wide margin. A second idea offers something stranger. In the first seconds after collapse, the newborn neutron star spins very fast and churns inside like boiling water. This churning, mixed with rapid spin, may work as a kind of dynamo, a natural engine that builds a field from motion. If the young star spins fast enough, the dynamo runs wild, and the field grows to magnetar strength before the star settles into stillness. If the star spins too slowly at birth, the dynamo never catches, and the star ends up as an ordinary pulsar instead. This might explain why only a small fraction of neutron stars become magnetars. It might also be wrong. The truth may sit somewhere between these two pictures, or in a third one we have not yet imagined. What is remarkable is that the raw material for all of this comes from the same cosmic story that made everything around you. The iron in the crust of a neutron star was fused inside an older star long before the collapse. That same kind of iron sits in the core of the Earth, giving our planet its own gentle magnetic shield. The carbon in your body, the oxygen in the air, the calcium in your bones, all of it was cooked inside stars and scattered by their deaths. A magnetar is not made of exotic material, invented from nothing. It is made of the ordinary ingredients of the universe, pressed into an extraordinary state. Even the water in the oceans traces back to the same web of stellar death and rebirth. Some of it likely arrived on comets, icy travelers left over from the birth of the solar system. Those comets were built from dust that had once drifted through the wreckage of dying stars. When you look up at the night sky and picture a magnetar spinning quietly out there, you are looking at a cousin of the matter in your own cup of tea. The elements are shared, only the pressure, the density, the field strength are almost impossibly different inside a magnetar. This shared matter behaves in ways we cannot test in any lab on Earth. Asia. An iron atom near the surface stretches into a long, thin shape, pulled by the field into something more like a needle than a sphere. Electrons no longer drift freely. They move only in tight, narrow paths, herded by lines of force we cannot see. Chemistry, as we know it, breaks down. What replaces it? We can only guess. Some models suggest sheets of iron so warped they form ridges. Others suggest a smooth, glassy skin. Which picture is correct depends on physics we do not yet fully understand. So the building blocks of a magnetar are, in a sense, deeply familiar and deeply strange at the same time. Ordinary atoms, extraordinary conditions, old dust from ancient stars wound into the tightest magnetic knot known to nature. And still, the question of exactly how it holds together hums quietly out there in the dark, waiting. The story of how we first heard the whisper of a neutron star begins in a quiet field in England in the late summer of 1967. A young graduate student was combing through long strips of paper covered in inked squiggles. These squiggles were radio signals from the sky, recorded by a new kind of telescope. Most of the marks looked like noise, but one small patch of scribbles kept returning night after night at exactly the same spot in the sky. It ticked. It ticked with a rhythm so steady that at first no one believed it could be natural. For a short while, the signal was gently nicknamed after little green men, because nothing in the known universe was thought to pulse that reliably. Stars did not tick, galaxies did not tick. Only a clock could tick like that. Yet the signal came from far beyond our solar system, from somewhere deep in the quiet dark between the stars. Within months, more of these tiny cosmic clocks were found, and slowly the truth began to settle in. These were not messages. They were the dying whispers of collapsed suns. The forces that make a neutron star tick are, in a way, the forces that shape everything we have been talking about. Gravity is the first. Gravity is what pulled the old star inward when its fuel ran out. Gravity is what crushed its core until protons and electrons melted together into neutrons. And gravity, even now, is what holds the tiny remnant together against its own furious spin. On the surface of a neutron star, gravity is so strong that a marble dropped from a meter above would strike the ground faster than any bullet ever fired on Earth. Balanced against that gravity is pressure, not the ordinary pressure of gas or liquid, but something stranger. Neutrons resist being packed too closely together. This resistance is called degeneracy pressure, a quiet outward push written into the rules of very small particles. Gravity presses in, degeneracy presses out, and in that hushed standoff, the star holds its shape, no larger than a small city, yet heavier than our sun. Then there is spin. When the old star collapsed, it kept the twirl it had before, the way an ice skater spins faster when she pulls her arms in close. A slow, lazy rotation over weeks became a fast rotation over seconds, then fractions of a second. Some neutron stars now turn hundreds of times each second. That spin carries with it the seed of the magnetic field, wound tight into the collapsing body like thread on a spool. And it is the magnetic field that turns a plain neutron star into something far stranger. As the star spins, its magnetic field spins with it. Charged particles near the surface are caught in that field and flung outward along the magnetic poles. They pour into space as narrow beams of radio waves, or X-rays, or gamma rays. If one of those beams happens to sweep across Earth as the star turns, we see a pulse, then darkness, then another pulse, a lighthouse in the sea of night. Why some neutron stars have modest magnetic fields and others have fields trillions of times stronger is a question we still cannot fully answer. One idea is that the difference lies in how fast the young star was spinning at the moment of collapse. A very fast spin might churn the interior like a dynamo, amplifying the field to unimaginable strength. Another idea is that certain kinds of collapsing cores are simply more turbulent, allowing the magnetic threads inside to twist and tangle into a much tighter knot. Both ideas have supporters. Neither has been proven. The truth may be some blend of the two, or something we have not yet thought of. Heat plays its own quiet role. A newborn neutron star is astonishingly hot, glowing at temperatures we can barely picture. Over millions of years, it slowly cools. As it cools, the crust hardens. The magnetic field, locked inside that crust, becomes strained. Sometimes the strain grows too great, and the crust cracks. What happens next, and how that cracking might release the star's most violent flares, is a story for a later section. For now, sit with that first discovery. A young researcher, a strip of paper, a ticking mark that should not have existed, somewhere 50,000 light years away. One of these strange collapsed suns had been sending its whisper across the dark for thousands of years before anyone here noticed. And in listening, we opened a door onto a family of objects whose deepest forces we are still learning to name. Picture a lighthouse standing on a rocky shore. Its lamp turns slowly through the fog, and a beam of light sweeps across the water in a steady rhythm. Sailors far out at sea see the flash come and go, and by that pulse they know where they are. A neutron star behaves in much the same way, though the scale is almost impossible to hold in the mind. A neutron star is only about 20 kilometers wide. That is roughly the size of a small city. You could drive across it in less time than it takes to finish a cup of tea, if such a drive were possible. And yet, packed into that tiny sphere is more mass than our entire sun. If you shrunk the sun down to a beach ball, a neutron star would be smaller than a marble sitting beside it. Now imagine that marble spinning, not slowly, the way a planet spins. A young neutron star can turn hundreds of times every second. Some rotate so fast that a point on their surface moves at a fair fraction of the speed of light. A grain of sand on the equator of one of these stars would travel farther in 1 second than a jet plane travels in an hour. From two opposite points on the star, narrow beams of radio waves stream out into space. These beams follow the star's magnetic field, which is tilted a little compared to the spin. So as the star turns, the beams sweep around like the lamp in that lighthouse. If Earth happens to lie in the path of one of these beams, we see a pulse, then nothing, then another pulse, perfectly timed, astonishingly precise. Some pulsars keep time better than the finest atomic clocks built on Earth. A pulse might arrive every 1.5 seconds, or every 300ths of a second, and it will arrive that way for years and decades, and perhaps centuries. The regularity is so clean that when the first pulsar was found, some researchers wondered, only half joking, whether a signal that steady could really come from nature at all. The scale of these beams is difficult to imagine. Picture standing at the edge of a field on a still night, somewhere thousands of light years away. A small, dense star is turning, and a thin cone of radio light is sweeping the galaxy. That cone brushes across our tiny blue world for a fraction of a second, and a large dish antenna somewhere on Earth catches a whisper of it. Then the beam moves on, out into the emptiness beyond us, and will never return along quite the same line again. The distances involved dwarf anything human. Light from some of these pulsars set out before the pyramids were built. It traveled across cold, quiet space, past drifting clouds of hydrogen, past other stars living and dying, and finally reached a small receiver on the third planet from an ordinary yellow sun. The pulse we hear tonight is a pulse the star gave off long before anyone was listening. Magnetars, the strange cousins of ordinary pulsars, follow the same lighthouse pattern, but their beams carry far more force. Their magnetic fields are thought to be 1,000 times stronger than those of the fastest radio pulsars, and perhaps 1,000,000,000,000 times stronger than the magnet that holds a photo to your refrigerator. That number, a 1 followed by 15 zeros, is easy to write and impossible to feel. It helps a little to say it this way. If Earth's magnetic field were a whisper, a common pulsar would be a shout, and a magnetar would be a sound loud enough to shake a mountain into dust. Yet even here the mystery holds. We do not fully know why some neutron stars beam so cleanly, like careful lighthouses, while others flare and sputter and fall silent for years. One idea is that the geometry of the magnetic field decides everything, and that a well-aligned magnetar simply cannot sustain the neat pulses of an ordinary pulsar. Another view is that the interior of the star, still hidden from us, drives the difference through processes we have not yet named. Both ideas remain open. Both may turn out to be partly right or partly wrong. For now, it is enough to picture that turning marble far away, sweeping its narrow light across the dark ocean of the galaxy. Somewhere out there, a beam is moving through empty space at this exact moment, headed toward a place that will not exist for another 10,000 years. The lighthouse keeps turning. The mystery keeps its own quiet time. Float, for a moment, just above the surface of a magnetar. You could not do this in truth, of course. The field around you would already have unmade the atoms in your body long before you arrived. But in imagination, in the safe dark of your room, you can drift there and look down. What you would see is a sphere so small it hardly seems worth the trouble of stars. Perhaps 20 kilometers across, a single city wrapped around itself, spinning slowly or quickly, depending on the star's mood. Yet this small ball holds more matter than our sun. Its surface glows a dull, angry gold, hotter than any furnace we could ever build. The crust would look, at first, almost smooth, smoother than glass, smoother than the still surface of a frozen lake at dawn. This is because gravity here is so fierce that the tallest mountain a magnetar can hold up is only a few centimeters high. A ripple, a wrinkle. Nothing that would even catch your shoe. But smooth does not mean calm. The crust of a neutron star is not rock in any way you have ever known rock. It is a lattice of atomic nuclei, packed together in a rigid crystal, with a sea of free electrons flowing between them. Some researchers describe it as the strongest material in the universe, billions of times stronger than steel. Others are more cautious and remind us that we have never held a piece of it. We can only work from equations and hope the math is honest. Above that crystal shell hangs a thin atmosphere, not air, not gas as you would recognize it, perhaps only a few centimeters deep, a skin of ionized carbon or hydrogen or helium, stretched flat by the crushing pull below. The colors there would be strange. The magnetic field is so strong, it changes how light itself moves through the atmosphere. Photons that should scatter in one direction are steered in another. The glow would shimmer and stripe, banded like the surface of a hot metal, cooling too fast. Now imagine that this thin, smooth crust is under terrible strain. Deep inside the star, the magnetic field is twisted and knotted like a great ball of tangled thread. The field wants to relax. It pulls and tugs at the crust from below, and the crust, hard as it is, can only take so much. Then, without warning, something snaps. This is what some astronomers call a starquake, a sudden cracking of the outer shell. On Earth, an earthquake shifts the ground by meters. On a magnetar, the crust may shift by only a centimeter. But that tiny motion releases energy beyond anything our planet has ever produced. In the flash of an instant, more energy pours out than our sun gives off in 100,000 years. If you were floating there, you would not have time to see it. You would simply be gone. But if you could watch, safely, from far away, you might see the whole surface ripple, a wave of light and heat racing across the little sphere, the atmosphere lifting for a moment, then settling back. Perhaps a faint crackle of new patterns in the glow, where fresh magnetic lines have broken through from below. The starquake idea is one of the leading explanations for the sudden bursts of gamma rays we sometimes catch from magnetars. But it is not the only one. Some researchers wonder if the true source of these outbursts lies deeper still, in the churning liquid interior, where the magnetic field may reconnect and snap the way lines on the sun sometimes snap. Others suggest a mix of both, with the crust and the interior trading strain back and forth over centuries. The evidence is incomplete. We are, in truth, guessing at the skin of something we cannot touch. And so the picture we hold in mind is a strange one, a tiny, glowing sphere, a skin of iron-like crystal, smoother than any mirror, a whisper-thin atmosphere painted in bands of banded light, a hidden tension pulling at the whole shell from beneath. Silence for years or decades or centuries. Then, in a single heartbeat, a crack no wider than a fingernail, and a flash of light bright enough to be seen across half the galaxy. We do not yet know how often these events happen on any given magnetar. We do not know exactly what the crust is like just before it breaks, or how it heals afterward, or whether it ever fully heals at all. The surface of a magnetar remains, for now, a place we can only visit in the imagination, a place that trembles quietly in the dark, waiting for the next slow twist of the field to gather and finally give way. Now we sink beneath the crust of a special kind of neutron star, one that carries a name astronomers use with a certain quiet respect, A magnetar. The word simply means a neutron star with a magnetic field so strong that it becomes the dominant force shaping everything around it. Ordinary neutron stars are already extreme. Magnetars are extreme even by that impossible standard. And what lies inside them may be the most unexplored territory in modern astrophysics. From the outside, a magnetar looks much like any other neutron star. A small dark sphere, perhaps 20 kilometers across, wrapped in a thin glowing atmosphere of ionized gas. But the numbers hidden in that quiet shape are staggering. A typical refrigerator magnet holds a field of about 100 Gauss. The Earth's own magnetic field measures less than 1 Gauss at the surface. A neutron star may hold 1 trillion Gauss. A magnetar may hold 1,000 trillion. That is a quadrillion times stronger than the field guiding a compass needle in your hand. No one has ever measured such a field up close. No instrument built by human hands could survive the attempt. Everything we know about magnetars comes from the light they send us across thousands of light years, and from the slow, careful modeling of physicists trying to imagine what could possibly hold such power together. Here is where the puzzle deepens. A neutron star's magnetic field should, by the simple laws of induction, decay over time. The currents that carry it should slow. The field should weaken. And yet magnetars seem to keep their fury for tens of thousands of years, releasing sudden violent flares, then falling quiet, then flaring again. Something inside is feeding the field. Something is storing energy in the deep interior and letting it out in irregular bursts. What that something is remains one of the most stubborn open questions in the study of dead stars. One leading idea proposes that the field itself is twisted deep inside the star, wound tight like a coiled spring beneath the crust. As the crust slowly settles and shifts, the twisted field snaps into new configurations, releasing enormous energy in the process. In this picture, the magnetar is a slow engine, converting stored magnetic tension into flares of gamma rays and X-rays. The interior would be threaded with knotted, tangled field lines that no telescope can ever see directly. A competing view suggests something even stranger. Perhaps the interior of a magnetar is not merely a sea of neutrons at all. Perhaps, under such crushing pressures, the neutrons themselves break down into their component parts, the quarks that normally stay locked away inside every particle of ordinary matter. If a magnetar's core is a soup of free quarks, the rules for how magnetic fields behave in that soup are unknown. Some theorists wonder whether such a quark core could act as a kind of natural dynamo, generating and refreshing the field from the inside. Others doubt this picture entirely and argue that plain neutron matter with the right physics is enough. There is a third possibility that some researchers find compelling. The magnetar's fury may be inherited. In the seconds after the parent star's collapse, the newborn neutron star may have spun so rapidly and churned so violently that a runaway process amplified its field to unimaginable strength. Once frozen into the star's superconducting interior, that field simply stays. In this view, magnetars are not being fed. They are cooling giants, still holding the memory of their violent birth. Each of these ideas explains some observations and struggles with others. The Starquake picture matches the sudden bursts astronomers see. The quark core picture might explain why magnetars seem hotter than they should be for their age. The frozen field picture matches how rare magnetars are, since only a small fraction of collapsing stars would produce the right conditions. None of the three has won the argument, and the truth, as often happens in astrophysics, may weave elements of all three together. What sits at the very center of a magnetar remains genuinely unknown. No laboratory on Earth can reproduce the pressures involved. No spacecraft can approach one closely enough to sample the light from its deepest layers. We are left with distant flickers, careful mathematics, and the slow, patient work of comparing theory to observation. For tonight, it is enough to picture that hidden interior, a tightly wound field, invisible and immense, threaded through matter we cannot name. A silent engine, storing and releasing energy on its own strange schedule. A puzzle wrapped in a crust of iron, held together by forces the universe has not yet explained to us. The Magnetar keeps its secrets, and we keep wondering what they are. Everything in the universe seems to breathe in cycles. Stars turn on their axes, planets swing around their suns. Even light itself moves in gentle waves, rising and falling as it crosses the dark. A Magnetar is no different. It spins, it pulses, and it shapes the space around it in slow, steady rhythms that we are only beginning to trace. The first cycle is the spin. A young Magnetar turns once every few seconds, which sounds slow until you remember that the whole star is packed tighter than an atom's core. As it turns, its magnetic field turns with it, sweeping through the thin gas around it like a great invisible wing. Each rotation drags a little energy away. Over thousands of years, the spin slows, the field weakens, and the star settles into a quieter state. But there is a second rhythm hidden inside that first one, and it is far stranger. In a magnetic field, trillions of times stronger than anything on Earth, the shape of an atom begins to change. On our planet, atoms are roughly round. Electrons circle the nucleus in soft, spherical clouds. Push those atoms into a Magnetar's field, and the clouds get squeezed. They stretch out into thin, needle-like shapes, aligned with the field lines. Whole layers of matter would stand on end, like grass combed by an invisible hand. This is not a theory in the loose sense. The math is fairly clear. In fields this strong, ordinary chemistry stops working the way we know it. Atoms cannot form the same bonds. Materials cannot behave the way they do in our labs. The surface of a Magnetar, if we could stand near it, would be a place where the very rules of matter have been rewritten by the field. What remains open is how deep this rewriting goes. Some researchers wonder if the field reaches all the way to the star's core and organizes the matter there into strange layered structures. Others suspect the interior field is more tangled, twisted into knots that slowly unwind over centuries. Both ideas fit the observations we have. Neither has been proven. The cycles of a Magnetar's inner life may be gentle and orderly, or they may be chaotic in ways we cannot yet picture. There is also the cycle of eruption and quiet. A Magnetar does not burn steadily. It sits calm for years, sometimes decades, and then flares. A soft gamma repeater will send out short bursts of high-energy light again and again over weeks or months before falling silent. An anomalous X-ray pulsar glows in a slow, dim rhythm, brightening and fading in ways that do not quite match its spin. These patterns hint at something happening under the crust, a slow build of magnetic tension, released in sudden snaps. One idea is that the field itself is slowly rearranging inside the star. As it settles into a lower energy shape, it drags on the crust from below. The crust resists, then gives way, and the sudden shift releases a burst of energy we see as a flare. Another idea places the action higher up, in the twisted field lines that arch above the surface. In that picture, the loops of magnetic force tangle and snap like overstretched rubber bands, and the star itself stays mostly still. Both cycles may be happening at once. We do not yet know which one drives the biggest events. Then there is the longest rhythm of all. A Magnetar's monstrous field is not thought to last forever, over tens of thousands of years. It slowly decays, bleeding energy into the star and its surroundings. As the field fades, the flares grow rarer. The star cools. It settles into something closer to an ordinary neutron star, spinning quietly, its greatest violence long behind it. If this picture is right, every Magnetar we see is a young thing caught in a brief, fierce chapter of a much longer life. But there is a competing possibility. Some researchers suggest that a Magnetar's field can be refreshed from within, drawn up out of currents deep in the core. If so, the cycle might not be a simple decline. It might be more like a slow heartbeat, with fields rising and falling over ages we cannot measure from a single human lifetime. We watch these stars for years and see only a sliver of their rhythms. A flare here, a slow shift in brightness there, a tiny change in the pulse. Behind those small signs, whole cycles are turning that we have never seen from beginning to end. For tonight, it is enough to picture the field, patient and immense, slowly reshaping the atoms in its grip. Magnetars do not live in isolation. They share the sky with a much larger family of neutron stars, and most of that family behaves in a very different way. The quieter cousins are called radio pulsars, and they hum across the galaxy in slow, steady beats. To understand what makes a Magnetar strange, it helps to sit for a while with these calmer neighbors and to notice how thin the line between them really is. A radio pulsar is a spinning neutron star that sends out beams of radio waves from its magnetic poles. As it turns, the beams sweep across space like the light from a distant lighthouse. When one of those beams passes over Earth, our radio telescopes hear a soft tick, then silence, then another tick. The rhythm can be faster than a human heartbeat or slower than a lazy breath. Some pulsars spin hundreds of times each second. Others take several seconds for a single turn. The first radio pulsar was found in 1967, when a young researcher noticed a strange, regular pulse in the data from a new radio telescope. The signal was so precise that, for a short time, the team wondered if it might be artificial. It turned out to be nothing so simple. It was the ghostly heartbeat of a dead star, still spinning long after its outer layers had blown away. Since then, astronomers have catalogued more than 3,000 of these steady tickers scattered across the Milky Way. Compared to a Magnetar, a typical radio pulsar has a magnetic field that is almost gentle, still enormous by earthly standards, but perhaps 1,000 times weaker than the fields around their fiercer siblings. Their surfaces are quieter. Their crusts do not seem to shudder with the same violent starquakes. They spin down slowly, giving up their energy over millions of years in a slow, patient decline. If a Magnetar is a storm, a radio pulsar is a soft, distant rain, and yet the family resemblance is unmistakable. Both begin as the collapsed cores of dying massive stars. Both pack the mass of the sun into a sphere no wider than a small city. Both turn incredibly fast at birth. Somewhere in that shared history, a small difference in spin or in the tangling of magnetic field lines during the collapse seems to decide the whole future of the star. One idea is that the very first seconds after the supernova matter most. If it spins more slowly, the field stays modest, and the star settles into the calm life of a radio pulsar. Another view suggests that the parent star's own magnetic field is the deciding factor. In this picture, some massive stars carry unusually strong fields deep in their cores, long before they die. When they collapse, that field is squeezed inward with the rest of the matter, and the result is a Magnetar from the very first moment. The two ideas are not fully separate, and they may both be partly true. The evidence is still thin, and the moment of birth is hidden behind the blinding light of the supernova itself. The neighborhood grows even more interesting when you notice the in-between cases. Some neutron stars behave mostly like radio pulsars, but occasionally send out short, sharp bursts of X-rays, as if a magnetar were hiding inside. Others were classified as magnetars and quieted down, and now tick softly in radio like ordinary pulsars. The categories seem to blur at the edges. It may be that every neutron star carries the potential for both behaviors, and that what we see depends on which stage of its long life we happen to catch. There are other neighbors too. Some pulsars share their orbits with a companion star, drawing gas from its outer layers and spinning faster as they feed. Others drift alone through the dark, unlit by any partner, sending their small radio whispers into empty space. A few sit at the centers of the glowing clouds left behind by their birth explosions, still lighting up the wreckage from within. Each variation is a small clue about what a neutron star can become when its surroundings shift. Sitting among these quieter neighbors, the Magnetar begins to look less like a separate species and more like an extreme mood of the same underlying object. The question of why some neutron stars sing softly in radio while others rage with fields 1,000 times stronger remains open. Somewhere in the first seconds of collapse, the choice is made. We are still learning how to read it. For most of their long lives, neutron stars keep time better than almost anything else in the universe. A pulsar spinning many times each second can rival the accuracy of the finest atomic clocks built here on Earth. Astronomers point their radio dishes at these distant lighthouses and record pulses that arrive with such precision that the star itself becomes a kind of cosmic metronome. And yet, every so often, one of these perfect clocks skips. The rhythm shifts. The star spins up just a little, all at once, and then slowly settles back into its long, patient slowing. These small hiccups are called glitches, and they are one of the strangest things a neutron star can do. A glitch is tiny by human standards. The change in spin might be 1 part in a million, or 1 part in a billion, but for a body the size of a city packed with more mass than the sun, even that small jump takes a staggering amount of energy. Something inside the star has shifted. Something has released a burst of motion that was, until that moment, locked away, and no one on Earth can say for sure what that something is. One leading idea points to the strange inner layers of the neutron star. Deep beneath the iron crust, researchers think there is a sea of neutrons that behaves in a way no ordinary liquid does. It flows without friction. It spins in tiny quantized whirlpools called vortices, each one carrying a small piece of the star's rotation. As the outer crust slowly loses speed, dragged down by the star's magnetic field, the inner sea keeps spinning fast. The two layers begin to disagree, and when the tension between them grows too great, the vortices break free all at once, dumping their spin into the crust. The star jumps forward, the clock glitches. That is one theory. Another possibility is that the crust itself is to blame. As a neutron star slows over millions of years, its shape must very slowly adjust. A spinning object wants to bulge at the equator, and as the spin fades, that bulge should ease. But the crust of a neutron star is not soft. It is thought to be the strongest material in the known universe, billions of times stronger than steel. So the crust resists, holds its shape, and then, when the strain finally becomes too much, it cracks. A starquake ripples through the surface. The star's shape shifts by a fraction of a millimeter, its moment of inertia changes, and the spin ticks upward. Which of these two pictures is correct, or whether both play a part, remains an open question. Magnetars glitch too, and when they do, the events are often more violent. Sometimes a glitch in a magnetar is followed by a bright burst of X-rays, or by a stretch of unusual timing behavior that lasts for months. Sometimes the star spins up, and sometimes, more rarely, it spins down in a sudden anti-glitch that no one fully understands. The most extreme timing events ever recorded from neutron stars have come from these magnetized giants, and each new observation seems to add another puzzle rather than solve the old ones. The record holders are worth pausing on. Some pulsars have glitched by amounts so small they are barely detectable, drifting up by less than a part in a trillion. Others have jumped by nearly 1 part in 100,000, an enormous shift for a body so dense. The Vela pulsar, one of the most closely watched neutron stars in the southern sky, glitches every few years like clockwork, and each event delivers a new chance to peer indirectly into its hidden interior. The Crab pulsar glitches too, but more gently and with a very different pattern. Why one star glitches often and another rarely, why some prefer small jumps and others large ones, is not yet understood. What makes these hiccups so tantalizing is that they are one of the very few ways we can hear the interior of a neutron star speak. We cannot send a probe inside. We cannot recreate the pressure in any laboratory on Earth. All we can do is watch the pulses arrive and listen for the moments when the rhythm stumbles. Each glitch is a message, faint and encoded, from a place we may never visit. It tells us that something down there is moving, shifting, releasing, adjusting. It tells us the interior is not still, and yet the message arrives in a language we have not fully learned to read. The glitches happen, the models compete, the star spins on, keeping almost perfect time, hiding its secrets in the small imperfections of its beat. Let us slow down now and turn our attention to the small things, the quiet details, the features of a neutron star that never make the headlines, because they hide beneath the surface in layers so strange that we have no everyday words for them. Picture a sphere no wider than a small city, wrapped in a thin skin of iron. That skin is only about 1 centimeter or 2 thick, according to our best models, and beneath it, the star becomes something we can barely describe. The outer crust, just below that iron shell, is thought to be a lattice of atomic nuclei packed shoulder to shoulder on Earth. Atoms sit in loose arrangements with plenty of empty space between them. Inside a neutron star, gravity crushes that space away. The nuclei lock into a rigid pattern, like tiles in a floor, but a floor that is denser than anything you have ever touched. A single sugar cube of this material would weigh more than every car in a large city, combined. As we sink deeper, the picture grows stranger. The nuclei get heavier and heavier, packed with more neutrons than any element on Earth could hold. At some depth, the neutrons begin to leak out of the nuclei entirely. They drift free between the tiles, forming what some researchers call a neutron sea. This is a form of matter that has never been made in any laboratory, and probably never will be. It exists only here, in the crushed heart of a dead star. The details grow more delicate still. In this deep layer, the free neutrons are thought to behave as a superfluid. That means they flow without any friction at all. If you could stir them, they would keep swirling forever, in tiny vortices thinner than a human hair. Some theorists believe these vortices are pinned in place by the surrounding lattice, and that when they suddenly slip free, they cause the little glitches we discussed earlier. It is a lovely idea. It is also unproven. Other researchers wonder if the glitches come from the crust itself, cracking under stress, and the truth may be a quiet mixture of both. Deeper still, the pressure grows so severe that the neat lattice of nuclei can no longer hold its shape. The nuclei begin to smear together. They stretch into long tubes, or flatten into sheets, or curl into hollow bubbles. Physicists have given these shapes affectionate names, borrowed from the kitchen. They speak of spaghetti and lasagna, and gnocchi and Swiss cheese. Together, these shapes are called nuclear pasta. It is a strange name for what may be one of the strongest materials in the universe. Some calculations suggest nuclear pasta is 10 billion times stronger than steel. Whether it truly exists in the form we imagine, no one yet knows. Beneath the pasta layer, the star becomes almost pure neutrons, with a thin scattering of protons and electrons swimming through. And beneath that, at the deepest core, our knowledge simply runs out. We have models, we have equations, we have guesses, but the pressures there are so far beyond anything we can create on Earth that no experiment can confirm what happens. It might be a soup of quarks, the tiny particles that normally live locked inside protons and neutrons. It might be something even stranger, a form of matter no one has named yet. The magnetic field threads through all these layers like a rope woven through a stack of blankets. In the crust, the field is thought to be locked into the lattice, twisted and knotted by the star's slow evolution. In the superfluid interior, the field is thought to break into thin tubes, each carrying a single quantum of magnetism. When these tubes drift or tangle or snap, the surface of the star may shudder. This may be part of why Magnetars flare, though the full story is still being written. What makes these details so lovely is how small they are, and how much they matter. A crack no wider than a fingernail, in a crust just a centimeter thick, can release more energy in 1/10 of a second than the sun gives off in 100,000 years. A knot in a magnetic field, tied inside a sphere the size of a town, can flood the galaxy with light. The great mysteries of the Magnetar are not written in vast cosmic letters. They are written in the tiny textures of matter itself, in patterns we can only guess at from very far away. And so we sit with them tonight, quietly, letting the strangeness settle in without needing to solve it. Long before anyone had a name for it, the idea began with a simple question: what holds a neutron star together beneath its thin iron skin? In the years after the first pulsar signals reached Earth in 1967, a small group of physicists began asking what the crust of such a star might actually look like. They were not observing anything directly. They were working with pencils, paper, and slow calculations, trying to picture something no telescope could ever see. The neutron star had already surprised them once. It had matched a prediction made decades earlier, when the neutron itself was still a fresh discovery. The Swiss astronomer Fritz Zwicky and the German physicist Walter Baade had proposed back in the 1930s that a dying star might collapse into a ball of neutrons, packed as tightly as an atomic nucleus. Most of their peers found the idea strange, almost embarrassing. It sat quietly in the literature for 30 years, waiting. When the pulses finally arrived, the theory came back to life. And with it came a stranger question. If the interior of a neutron star is essentially one giant nucleus, then what happens near the surface, where the pressure is only almost unimaginable rather than fully unimaginable? What shapes would matter take in that in-between zone? The first serious answer came in the 1980s from the American physicists David Ravenhall, Charles Pethick, and James Wilson. They ran calculations on how nuclei would behave as you pressed them closer and closer together. At first, the nuclei stayed as tiny round beads, sitting inside a sea of loose electrons, but as the pressure grew, the beads began to touch. Then they began to merge. Then they began to stretch. The shapes that emerged from the math looked oddly familiar, round blobs, like tiny meatballs, long tubes, like spaghetti, flat sheets, like lasagna, twisted sheets with holes like bucatini or gyoza wrappers. The physicists, half joking and half serious, began calling these shapes nuclear pasta. The name stuck. Nuclear pasta is not a confirmed material. It is a prediction. No one has ever seen it, and no one may ever see it directly. It lives in the layer just beneath the crust of a neutron star, a shell perhaps only a few 100 meters thick, buried beneath a surface hotter than any furnace and stronger than any steel. Yet, if it exists, it may be one of the strongest known materials in the universe, tougher even than the diamond core of a crushed planet. That claim came from more recent simulations, run in the 2010s, by teams using supercomputers to model how these strange shapes would respond to stress. The results suggested that nuclear pasta could resist deformation to a degree that no earthly material comes close to. This matters for magnetars in particular. If the pasta layer is that strong, it could store enormous amounts of magnetic energy for long stretches of time, only releasing it when something finally cracks. Not everyone agrees. Some researchers argue that the pasta layer may be thinner than the models suggest, or that its shapes are less orderly than the neat drawings imply. Others wonder whether real neutron stars, with their swirling temperatures and tangled fields, ever settle into these clean geometric forms at all. The pasta might be more like a foam, or a slush, or something the human eye has no natural word for. Discovery, in this case, has been slow and quiet. There was no single telescope pointed at a single star that revealed the truth. There were papers and revisions and long conferences in ordinary rooms, and simulations that took months to finish. The instruments were not lenses or dishes. They were equations, tested against the tiny hints that neutron stars occasionally send us. A glitch in a pulsar's timing, a flare from a magnetar, a slow cooling curve traced over years. Each of these hints can be read in more than one way. A glitch might mean a starquake in the crust, or a sudden slip in the pasta below, or something else entirely. A magnetar's flare might come from a break in the outer shell, or from a deeper rearrangement in the pasta layer, or from the tangled field itself finding a new shape. The signals arrive, the theories multiply. The truth, so far, stays hidden. What is remarkable is how much of this picture was built without ever touching the thing itself. Humans learned about nuclear pasta the way ancient sailors learned about distant lands they never reached, by watching the shape of the waves that came back to shore. The waves, in this case, are pulses of radio, flickers of X-ray, and the slow arithmetic of gravity. Whether the pasta is true, somewhere out in the dark, a pulse of radio light travels for 1 billion years. It crosses empty space, drifts past sleeping galaxies, and finally brushes the antennas of a quiet telescope on Earth. The pulse lasts only a few thousandths of a second. In that tiny sliver of time, it carries as much energy as our sun gives off in days, or even years, and then it is gone. We call these strange flashes fast radio bursts, and for a long time, no one had any idea what made them. The first one turned up in old data in 2007. A scientist looking through recordings from a radio telescope in Australia noticed a single sharp spike that did not match anything nearby. It had the fingerprint of something very far away. At first, Many researchers wondered if it was a mistake, maybe a stray signal from a microwave oven in the break room, maybe a glitch in the machine. But then more of them showed up, from different telescopes, on different nights, in different parts of the sky. The strange thing is how small the source must be. A burst that lasts only a millisecond must come from an object no larger than a few hundred miles across. That is roughly the size of a city or a small country. Yet the energy is enormous, brighter than whole galaxies for a heartbeat. Only a handful of objects in the universe are that compact and that powerful. Neutron stars are one of them. Magnetars are an even better fit. In 2020, something remarkable happened. A magnetar inside our own galaxy, only about 30,000 light years away, let out a short burst of radio light. When scientists measured its shape and brightness, they found that it looked very much like a weaker cousin of the distant fast radio bursts. For the first time, there was direct evidence that at least some of these flashes come from magnetars. Many researchers felt a small, quiet thrill. A puzzle that had lasted more than a decade suddenly cracked open, just a little. But the mystery is not solved. That single galactic burst was thousands of times weaker than the brightest fast radio bursts seen in distant galaxies. Magnetars might explain the softer ones. Yet the truly enormous flashes, the ones that light up half the observable universe for a moment, may need something more. Some researchers think a young, unusually violent magnetar could still be the answer. Others wonder if two neutron stars grazing each other in orbit could produce the effect. A few have suggested collapsing objects we have not yet named. Then there is the question of the repeaters. Most fast radio bursts flash once and never return, but a small number of sources send burst after burst, sometimes over months, sometimes in strange clustered patterns. One repeating source seems to cycle roughly every 16 days, quieting down and then flaring again. No one is sure why. One idea is that the magnetar sits in orbit around another star, and the flares only escape when the geometry is right. Another idea is that the magnetar itself wobbles slowly, its beam swinging in and out of view. A third possibility is that something in the dense cloud of gas around it opens and closes like a shutter. Each idea has its own problems. Each idea has its own quiet appeal. What makes fast radio bursts so hard to pin down is how far away most of them are. The light we catch has traveled for hundreds of millions, sometimes billions of years. By the time it arrives, whatever made it may be long since changed or gone. We are looking at ghosts, in a way. We know the flash happened. We can even guess which galaxy it came from. But standing at the actual source, in real time, is far beyond us. There is a strange comfort in that. The universe keeps sending these tiny letters from unimaginable distances, and we keep collecting them without quite knowing who mailed them. Every year, telescopes find hundreds more. New instruments are being built that will find thousands. Somewhere in that flood of data, patterns may emerge that finally name the sources, or the patterns may only deepen the puzzle. For now, the working guess is that magnetars, or something very much like them, account for many of these bursts. The rest may belong to processes we have not yet imagined. When you hear the phrase fast radio burst, picture a small, dense star, twisted by a field beyond all reason, sending a single spark across the emptiness. That spark, faint by the time it reaches us, still carries a question we cannot quite read. Somewhere in the quiet dark between stars, two neutron stars sometimes find each other. They may have been born together, twin cores left behind after their parent stars died in twin explosions, or they may have drifted into each other's pull over long ages, Two lonely wrecks caught in a slow gravitational dance. Whatever brings them together, their story ends the same way. They circle, they fall inward, and after millions or billions of years, they touch. The dance is slow at first. Two dead suns, each no wider than a small city, glide around each other in wide orbits. Space itself carries away a tiny bit of their energy with every turn. This is one of the strangest ideas in modern physics. Moving masses send out gentle ripples in the fabric of space, and those ripples steal motion from the pair. So the orbit tightens. Year by year, the two stars creep closer. The circles shrink. The music speeds up. Near the end, everything changes. In the final seconds, the two neutron stars whip around each other hundreds of times per second. Their surfaces begin to feel each other's pull. Tides rise on their crusts, ridges of impossibly dense matter, lifting and cracking. If either star carries a strong magnetic field, that field is dragged, stretched, and twisted by the motion of the other. Some models suggest the fields can braid together, coiling into a shape that stores enormous energy. What that energy looks like when it releases, no one has fully seen. Then the merger. In an instant, two dead cores become one hot, spinning object. What is born in that flash is one of the deepest open questions in this whole story. Some researchers think the collision makes a heavier neutron star that survives, at least for a while. Others suspect the object is too heavy to hold itself up, and it collapses almost at once into a black hole. A third view sits in between, imagining a short-lived giant that spins fast enough to hold on for a few seconds, then folds inward. The evidence so far points to different outcomes in different mergers. The rules that decide which path a merger takes are not yet clear. This is where our topic ties into the wider symphony of the cosmos. A magnetar alone is already a puzzle. Two neutron stars meeting in the dark connect that puzzle to almost every other question in astrophysics. Gravitational waves ride outward from the crash and stretch space across the whole sky. Astronomers on Earth felt one such ripple in 2017 from a merger far across the universe. Light from that same event arrived shortly after, in gamma rays, then in slower colors that faded over weeks. For the first time, one cosmic event was heard in gravity and seen in light at the same time. The question of what magnetized neutron stars really are became part of a larger conversation about how the universe speaks to itself. The magnetic fields matter here in a way that is still being sorted out. If one of the merging stars is a magnetar, or if the merger makes a new magnetar in its wake, the field could shape everything that follows. Some models suggest a freshly born magnetar could pump energy into the wreckage for hours or days, changing the colors and brightness we see from Earth. Other models leave the field out and explain the same signals differently. The community has not yet agreed on which picture fits best. Every new merger the detectors catch is a fresh test of these ideas. There is a gentler connection too. The elements made in these collisions do not stay locked in the wreck. They spread outward in a slow glowing cloud, joining the drifting dust and gas between stars. In time, that cloud may fall into a forming solar system. The gold in a wedding ring may have started in a merger like this, billions of years ago and many light years away. If magnetic fields helped shape the wreckage, then the strange physics of magnetars may quietly touch the ordinary matter around us. So the picture grows. A single magnetar is a lonely lighthouse. A pair of neutron stars meeting in the dark is a conversation between two lighthouses, sending signals in gravity and in light, seeding the galaxy with heavy metals, and perhaps birthing new magnetars in their wake. What exactly happens in those final moments? And what kind of object rises from the crash, remains one of the open frontiers of this field. The mergers keep happening in the dark. The detectors on Earth keep listening. And the answers, when they come, will be pieced together from ripples we can barely feel. When two neutron stars come together in that final silent embrace, something strange and beautiful happens in the fraction of a second before they merge. The immense tidal forces tear at their crusts. Streams of neutron-rich matter spray outward into space, glowing faintly at first, then flaring as the material decays. In those spraying jets, in that hot expanding cloud, atoms far heavier than iron begin to form. Some of the gold in the ring on a finger, some of the silver in a spoon, some of the platinum in a wedding band may have been forged in exactly this kind of ancient collision, long before the sun was born. This idea is fairly new to astronomy. For a long time, researchers thought that all heavy elements came from ordinary supernovae, the explosive deaths of massive stars. But the numbers never quite worked out. Supernovae produce plenty of iron and lighter metals, yet they struggle to account for the amount of gold, platinum, uranium, and other heavy elements scattered across the galaxy. Something else had to be making them. One leading idea pointed to neutron star mergers as the missing forge. And in 2017, when astronomers observed a merger through both gravitational waves and light, they saw the telltale glow of freshly minted heavy elements in the afterglow. The theory gained real ground that night, yet the picture is still incomplete. Some researchers wonder whether neutron star mergers alone can produce all the heavy elements we see, or whether other rare events also contribute. There is a competing hypothesis involving certain kinds of magnetically driven supernovae, where rapidly spinning, strongly magnetized cores may fling out neutron-rich material of their own. Magnetars, or the objects that become magnetars, might play a role in these unusual explosions. Whether the gold in the universe comes mostly from mergers, mostly from these special supernovae, or from some balance of both, is a question still being worked through. What is clear is that these events change the galaxy slowly, patiently, across billions of years. Each merger, each collapsing core, enriches the gas clouds drifting through interstellar space. New stars form from that enriched gas. Planets condense around those stars, carrying traces of the elements built during long ago cosmic violence. The iron in a mountain, the copper in a wire, the calcium in a bone, all of it was assembled inside stars that no longer exist. Sometimes in the strange final moments of objects like neutron stars and magnetars, the changes never stop. Right now, somewhere in a distant galaxy, two neutron stars are spiraling toward each other. Their orbits are shrinking by tiny amounts every year, radiating away energy in the form of ripples in space itself. In a few million years, or 100 million, they will meet. When they do, they will paint their little corner of the universe with fresh, heavy elements. Meanwhile, magnetars are quietly losing their magnetic strength across thousands of centuries. The fields that once measured a quadrillion times Earth's decay, slowly feeding energy into radiation and flares. A magnetar that is fierce today may be nearly silent in 100,000 years. Its crust cool, its field faded, its glow dimmed to something ordinary. The transformations run both ways. Old neutron stars fade. New ones are born from the collapsing cores of dying massive stars. Every so often, one of them is born spinning strangely fast or wrapped in a strangely intense field, and it becomes a magnetar rather than a quiet pulsar. Why some collapsing cores make magnetars while most do not is another open question. One idea suggests that a special kind of internal churning during birth, a dynamo effect, amplifies the field enormously. Another view holds that magnetars inherit their strength from the magnetic history of the star that came before. The evidence does not yet clearly favor one story over the other. What we do know is that the universe is a slow forge. It has been assembling heavier and heavier elements ever since the first stars ignited. The heavy metals in your hand, in the soil, in the seas, are the leftover ash of long collisions and quiet collapses. And when a magnetar merges with a companion, or explodes in some unusual way, it may add its own contribution to that great slow enrichment. The gold and silver of the cosmos are not static. They are still being made, still being scattered, still being pulled together into new worlds. For tonight, it is enough to picture that expanding cloud, warm colors fading into the dark, fresh atoms drifting outward, a galaxy just a little richer than it was the moment before, because two dense hearts finally found each other in the quiet of deep space. Light behaves strangely near a magnetar. It bends, it splits, it sometimes refuses to travel in the ways we expect. To understand what these fields would do to ordinary matter, we first have to understand what they do to the very idea of light, and then to the atoms that light passes through. The picture that emerges is quiet, strange, and still full of gaps we cannot fill. Picture the surface of a magnetar as a smooth iron shell, glowing a deep red around it. Invisible but everywhere, the magnetic field presses down with a force we have no way to test on Earth. In a laboratory, the strongest steady magnets we can build are millions of times weaker than the field near a magnetar's surface. The gap between what we can measure and what a magnetar holds is so wide that our best theories become guesses at the edges. In such a field, empty space itself may stop behaving like empty space. Physicists have long suggested that a vacuum near a magnetar becomes birefringent, meaning it splits light into two paths depending on how the light wave is oriented. On Earth, only certain crystals do this. Near a magnetar, the vacuum may do it on its own. Observations of one nearby neutron star in 2016 hinted that this effect might be real. But the evidence remains thin, and other explanations have not been ruled out. The question is still open. Closer to the surface, atoms would no longer look like atoms. On Earth, an atom is roughly round, with electrons drifting in soft, cloudy shells. Inside a magnetar's field, those clouds would be crushed sideways into thin, stretched shapes, like tiny needles pointing along the field lines. Chemistry, in any sense we know, would not exist. Water could not form. Rock could not form. The gentle rules that let a leaf hold its shape or a hand hold a cup would simply not apply. This is what people mean when they say a magnetar's field could erase a human body. It would not burn or crush in the ordinary sense. It would rewrite the shapes of the atoms themselves long before you ever touched the surface. Some estimates suggest that at a distance of 1,000 kilometers, ordinary matter would already begin to fail. Other estimates place the danger zone farther out. Both agree that the effect is not violent in the usual sense. It is quieter than that, and stranger. The atoms simply stop being the atoms we know. The light that escapes a magnetar carries hints of this hidden physics. Its X-rays arrive polarized, meaning their waves are lined up in preferred directions. A telescope launched in 2021 has begun measuring this polarization in detail, and the early results seem to match, at least in part. The idea that the vacuum near these stars is behaving in the way theory predicted decades ago. Yet, the match is not perfect. Some magnetars show polarization patterns that current models struggle to explain. Whether the surface itself is a solid crystal of iron, or a thin gas hovering above a stranger interior, remains debated. There is also the question of color, though color is not quite the right word for what a magnetar emits. Most of its light lives in X-rays and gamma rays, far beyond what human eyes can see. If we could translate that light into visible tones, the surface might glow a deep, patient red, while thin flares of harder radiation would flicker in shades our eyes have no name for. The visible light that does escape is faint, buried beneath the harsher glow above it. And then, rarely, a magnetar releases a burst so bright it briefly outshines every other X-ray source in the sky. One such burst in 2004 came from a magnetar roughly 50,000 light-years away, and yet it still nudged the outer edge of Earth's atmosphere, changing its ionization for a few moments, a gentle nudge across an unimaginable distance from a single trembling star. What that light was doing on its way here, passing through fields and vacuum and gas, is something researchers are still trying to piece together. For tonight, it is enough to picture it. A small, dense sphere, wrapped in a field we cannot recreate, bending light in ways we barely understand, reshaping atoms in silence. The physics of that surface is not settled. The behavior of that vacuum is not settled. Even the color, if we could see it in full, is a matter of theory as much as measurement. The mystery sits quietly, waiting for better instruments and better mathematics, glowing softly in the dark, in a language of light that we are only beginning to learn how to read. Space is often called silent, and in a strict sense it is. Sound needs a medium: air, water, rock, something for the wave to push against. In the empty vacuum between stars, there is nothing for a wave to travel through. And yet, when astronomers listen to a magnetar, they hear something, not with their ears, but with radio dishes, X-ray telescopes, and gravitational wave detectors that translate faint signals into patterns we can turn into sound. The first sound a neutron star makes, in this translated sense, is the steady tick of its rotation. A young pulsar can spin many times each second, and each sweep of its lighthouse beam across our telescopes registers as a soft pulse. Play those pulses through a speaker, and you get a clean rhythm, like a slow metronome or a gentle heartbeat. Some spin so fast the pulses blur into a low hum, a single tone drifting through the receiver. A magnetar sings a different song. Its rotation is slower, often just once every few seconds, and its voice is deeper and more ragged. Beneath that slow tick, though, lies something stranger. When a magnetar's crust shifts, a starquake as some researchers call it, the whole star rings like a struck bell. Instruments have recorded these oscillations, faint tremors in the light that pulses toward Earth, and when scientists shift those frequencies up into the range of human hearing, they sound like the low chime of a gong that keeps ringing long after it was struck. No one is entirely sure what makes the star ring in exactly the patterns we see. One idea is that the vibrations travel through the crust like waves through a thin metal shell. Another idea is that the ringing comes from deeper inside, from the strange fluid ocean of neutrons that fills most of the star's volume. A third possibility is that the crust and the interior ring together, coupled by the magnetic field itself, so the whole star behaves as one great trembling instrument. Which of these pictures is correct remains an open question. The magnetic field adds its own voice. When the field shifts and snaps, it can drive waves of charged particles that show up in radio data as crackles, whistles, and soft roars. Some magnetar flares produce a sudden burst followed by a long fading tail of pulses that, when translated, sound almost like slow breathing. In the great flare of December 2004, A Magnetar tens of thousands of light years away lit up detectors around the Earth and briefly disturbed the upper atmosphere. If you turn the light curve of that event into sound, it begins with a sharp crack and then settles into a rhythmic pulse that lasts for minutes as the wounded star spins and the burning region rotates in and out of view. Beneath these bursts lies a slower song, one that plays out over thousands of years. A Magnetar's magnetic field is thought to slowly decay, bleeding energy into the star's crust and out into space. As it decays, the star's spin slows. The bright, fierce pulsar of its youth becomes a quieter, dimmer object. The tick grows longer, the voice grows softer. Eventually, some researchers believe, the star fades below the threshold at which we can detect it at all. A silent cinder, still dense, still magnetic, but no longer singing. Whether every Magnetar follows this path is not yet settled. Some models suggest that the field decays smoothly, like a battery running down. Others suggest a more sudden shift, with the field collapsing in bursts as the crust rearranges itself. A few researchers wonder if some Magnetars may skip this quiet ending entirely, ending their lives in a different kind of collapse. The evidence is incomplete, because we can only watch these stars for a few decades, while their lives last for many thousands of years. Listening to a Magnetar then is like listening to a bell whose ringing spans ages. The fast pulses are the surface. The oscillations are the shivering skin of the star. The flares are the sudden strikes, and underneath all of it, too slow for any human lifetime to hear directly, is the long fade of a spinning giant losing its voice to the dark. For tonight, it is enough to imagine that slow music. A distant object turning in the vacuum, ringing softly to instruments that did not exist a century ago, telling a story we have only begun to translate. Somewhere out there, a Magnetar is ringing right now, and we are still learning how to listen. There is a quiet kind of beauty in the math that describes a neutron star. The numbers are strange, but the rules behind them are simple. A neutron star spins, and its spin can be measured with a precision that few things in nature allow. Some rotate hundreds of times each second, others turn slowly, once every 10 seconds, or once every 100. Yet whatever their speed, they hold to it with the steadiness of a fine clock. If you know the rate today, you can often predict where the beam will point a year from now, down to the second. This is where the mystery gets interesting. A neutron star is not always alone in space. Many of them travel with a partner, another star bound to them by gravity. The two of them trace slow ellipses around a shared center, like two dancers holding opposite ends of an invisible rope. And because the pulses from the neutron star are so regular, any tiny shift in their timing tells us something about the orbit. If the star drifts a little closer, the pulses arrive a little sooner. If it drifts away, they arrive a little later. From these small delays, astronomers reconstruct the whole hidden path. The math for this comes from ideas that are hundreds of years old. Ellipses, focal points, the sweep of equal areas in equal times. The same rules that describe a comet swinging around the sun also describe two dead stars whispering to each other in the dark. What changes is the scale. The gravity is fiercer. The orbits are tighter. Sometimes two neutron stars circle each other once every few hours, drawing closer with every pass, losing a trickle of energy to ripples in space itself. Those ripples are called gravitational waves, and their existence was predicted long before anyone could detect them. The prediction came from equations written on paper, and for decades the equations sat there, waiting. Then the timing of a binary pulsar was measured carefully enough to show that the orbit was indeed shrinking and shrinking at exactly the rate the equations foretold. The numbers match the sky. That match is one of the quiet wonders of modern science. Some neutron stars have companions we cannot see at all. The visible partner is dim or absent, yet the pulses still shift in a rhythm that betrays a hidden mass. Astronomers infer the size and orbit of the unseen body from timing alone. It might be a white dwarf, the ember of an ordinary star. It might be a planet. It might be another neutron star, dark and silent. The pulses trace the shape of something we cannot photograph, like a hand drawing an outline around empty air. The first planets ever found outside our own solar system were discovered this way, orbiting a pulsar. Their existence was pulled out of tiny variations in the arrival of radio ticks. No image, no glow, only the arithmetic of delayed pulses. And yet, the planets are real, small worlds turning around a stellar corpse, kept in place by rules any student can learn. What remains open is what the mathematics cannot yet reach. The orbits we can measure, the masses we can estimate, but the inside of the neutron star, the exact state of the matter beneath its crust, still resists our equations. Some models predict one relationship between mass and size. Other models predict another. When two neutron stars finally spiral together and merge, the shape of the gravitational wave they release depends on what they are made of. So each merger becomes a kind of test, a chance to compare theory against reality. So far, the results narrow the possibilities without closing them. For magnetars, the math is even less complete. Their fields decay over time, but the rate of decay is still argued. Their spins slow down, but by amounts that vary from one object to the next. The equations that describe an ordinary pulsar do not quite fit them. Something extra is happening inside, and that something has not yet been written down in a form everyone agrees upon. Still, the numbers we do have are enough to fall asleep wondering about. A neutron star that spins 600 times a second, a companion that circles it once every 2 hours, a distance measured in tens of thousands of light years, yet a timing accurate to a fraction of a millisecond. The universe, at these scales, keeps a rhythm we can almost hear. The rules are simple, the consequences are strange. And somewhere in the gap between what the math predicts and what the stars actually do, the deepest mysteries of these objects continue to wait. A magnetar is a place of impossible contradictions. Its outer skin can glow at temperatures near 1,000,000 degrees, hotter than the core of most stars, and yet, deep inside, in the quiet layers below the crust, the matter may be so ordered, so tightly packed, that it behaves almost as if it were frozen. The same object holds both extremes at once. It is one of the strangest balancing acts in nature, and the balance is more delicate than it looks. Think for a moment about how carefully our own world is tuned. Earth sits at just the right distance from the sun for water to stay liquid. Our atmosphere is thin, only a few tens of miles of breathable air, yet it holds in warmth and shields us from the worst of the sun's rays. Our magnetic field, generated by molten iron churning far below our feet, deflects the solar wind and keeps our air from being stripped away. Change any of these by a small amount, and the world we know would not exist. A magnetar is tuned even more finely and in far more violent ways. Its magnetic field is thought to reach strengths 1,000 trillion times stronger than the field around Earth. Some estimates place the strongest at a quadrillion Gauss, though the true peak values remain uncertain. That field is what holds the star's outer story together. It shapes the crust, it channels the heat, it locks the particles into strict patterns. Take the field away, and the Magnetar would relax into a more ordinary neutron star. Push the field even higher, and the star might tear its own crust apart. Inside, the temperatures are staggering. The core may sit at hundreds of millions of degrees for much of the star's life. Yet, in the language of physics, that same core is considered cold. This sounds like a contradiction, and in some ways it is. Neutron star matter is so dense that the particles inside behave as if they were near absolute zero. Even while glowing with enormous heat, the particles fill every available quantum state, packed like books in a shelf with no gaps. Physicists call this a degenerate state. It is a strange middle ground, neither the frantic dance of a normal hot gas, nor the stillness of true cold. The balance depends on many things staying just so. The mass of the star must sit within a narrow window, too little mass, and it would never have collapsed into a neutron star at all. Too much, and gravity would pull it further, crushing it into a black hole. The Magnetar sits on a knife edge between these two fates. Some researchers think a few Magnetars may already be leaning toward that edge, holding on by a small margin. Others think the balance is more forgiving, that a Magnetar can carry more mass than we suspect. The question remains open. The rotation matters too. When a Magnetar is young, it spins quickly, sometimes several times a second. That rotation helps generate and sustain the magnetic field, though the exact mechanism is still debated. One idea is that a rapidly spinning newborn neutron star acts like a dynamo, twisting weaker seed fields into monstrous ones during the first seconds of its life. A competing view holds that most of the field is inherited from the parent star and simply concentrated as the core collapses. Which idea is closer to the truth is still uncertain, and it may be that both play a role. Even the crust is a delicate thing. It is perhaps a mile thick, made of iron nuclei arranged in a crystal so stiff it may be the strongest material in the known universe. That crust holds the magnetic field lines in place. When it cracks, even slightly, the field lines snap and rearrange, releasing enormous bursts of energy. If the crust was softer, the field might slip and drift, and the Magnetar would fade more quickly. If the crust was stiffer still, the tension might build until the whole star tore itself open. Somehow, the balance holds for thousands of years. It is remarkable that any of this works at all. Everything about a Magnetar seems poised on the edge of some greater collapse or transformation, and yet these strange objects sit in the dark of the galaxy, quietly holding their contradictions in place, hot and cold at once, still and violent, ordered and wild. We do not fully understand how they keep the balance. We only know that they do, at least for a while, until something small shifts, and the star trembles and the balance is remade. Even after decades of listening, so much of what we hear from Magnetars remains unexplained. Our telescopes gather signals in radio waves, in X-rays, in gamma rays, and in the faint tremble of gravitational waves. Some of these signals fit our models nicely, others do not. And it is the ones that do not fit that keep researchers awake at night, or perhaps, more gently, keep them wondering during the quiet hours. Take the fast radio bursts. These are brief, brilliant flashes of radio light that arrive from far across the universe. Each one lasts only a few thousandths of a second. In that tiny sliver of time, the source releases as much energy as the sun gives off in days. Some of these bursts come only once, others repeat, arriving from the same distant point again and again, in patterns we cannot yet predict. In 2020, a fast radio burst was traced to a Magnetar inside our own galaxy. That was a beautiful clue It suggested that at least some of these bursts come from magnetars, but it did not close the case. Many fast radio bursts are far too bright to be explained by any magnetar we understand. So one theory is that different kinds of fast radio bursts come from different kinds of sources. Another theory is that magnetars can, under rare conditions, release far more energy than we thought possible. Both ideas remain open. There are also the quiet magnetars, or rather magnetars, that seem to go quiet for years and then suddenly wake. A source may sit still and dim for a decade, then flare with a burst of X-rays, then fall silent again. What sets the clock inside them? One idea is that stress builds slowly in the crust, like a spring being wound, until the crust finally cracks. Another idea is that the tangled magnetic field lines deep inside the star slowly rearrange themselves, and each rearrangement releases a pulse of energy at the surface. We do not know which picture is closer to the truth. It may be both, it may be neither. Then there is the puzzle of the giant flares. Only a handful have ever been recorded. In each case, a magnetar released a burst of gamma rays, so intense that it briefly outshone every other source of gamma rays in the sky. One such flare, from a magnetar roughly 50,000 light-years away, reached Earth in 2004 and gently pushed on the outer edge of our atmosphere. It was not dangerous to us. It was a soft touch from very far away. But we still cannot fully explain what triggers these flares. The leading idea is a sudden, violent reconnection of magnetic field lines above the surface, similar to what happens on the Sun, but on a scale beyond imagination. A competing idea is a deep crustal fracture that shakes the field from below. The evidence points in both directions at once. There are also signals we cannot yet place at all. Faint, slow pulses at odd frequencies, sources that pulse once every few minutes, far slower than a normal neutron star should be able to. Recently, astronomers have found objects that spin so slowly they should not be able to emit radio waves under any model we currently accept. And yet they do. Are these magnetars in a strange late stage of life? Are they a new kind of object entirely? The question is genuinely open. We do not yet know how a magnetar's field decays over time. We think it fades across thousands of years. But the rate is unclear, and so is what happens to the star underneath. Does the star become a quieter neutron star, indistinguishable from its cousins? Or does something inside it change permanently, leaving a fingerprint we might one day learn to read? We do not know if magnetars ever collide with each other. If they did, the merger would send out gravitational waves shaped in a way we have never seen. We are listening. We have not yet heard one for certain. And beneath all of these open questions is the deepest one. We still do not know what the inside of a magnetar is truly made of. The pressure and the magnetic field together create conditions no laboratory on Earth can copy. So the interior is a country we can only visit through equations and guesses. Some of those guesses will turn out to be right. Some will turn out to be beautifully wrong. Both possibilities are gifts in their own way to anyone who loves an unfinished puzzle. The signals keep arriving, softly, from the dark, waiting for us to understand them. Deep inside a magnetar, past the iron crust, past the neutron sea, past the strange lattice we call nuclear pasta, there may be a place where matter forgets what it is. The pressure there is so great that no experiment on Earth can match it. And in that unreachable center, neutrons themselves may break apart. Each neutron is built from 3 tiny pieces, called quarks. Under normal conditions, quarks stay locked inside their neutrons, bound so tightly that we have never seen a free one. But at the heart of a neutron star, some researchers wonder if that binding might finally fail. If it does fail, the core would become something new, a sea of loose quarks, packed shoulder to shoulder, flowing freely in a way no other matter can. Physicists call this a quark star, or sometimes a strange star, depending on which flavors of quark end up in the mix. No one has confirmed that such a thing exists, but no one has ruled it out either. The math allows it. The pressures inside a magnetar are almost certainly high enough. What we lack is a way to look. The trouble is that a quark core would be hidden beneath kilometers of ordinary neutron matter. From the outside, a quark star and a normal neutron star would look nearly the same. Both would be small, dense, and spinning. Both could carry a magnetic field. The only clues would be subtle. A quark star might be slightly smaller than a neutron star of the same mass. It might cool at a different rate. It might vibrate with slightly different frequencies after a starquake. These are faint signals, buried in noise, and we are only beginning to learn how to read them. Now imagine the future. 1,000,000 years from now, the magnetar we are wondering about tonight will have changed. Its magnetic field will have faded, its spin will have slowed, its bright outbursts will have quieted into a long silence, but its core, if it holds quark matter, will still be there, cold and locked away. In 1,000,000,000 years, the star may have cooled so much that it no longer glows at all. It will drift through the galaxy as a dark, silent ball, still carrying its ancient secret inside. The galaxy itself will change around it. Some stars will die. New ones will form from the gas the dying stars leave behind. Occasionally, one of those new stars will end its life the way this one did, in a collapse that leaves another dense heart behind. Over billions of years, the galaxy will fill with these quiet remnants. Some will be normal neutron stars, some perhaps will hold quark cores, and a few, if certain theories are right, may be pure quark stars all the way through. Smaller cousins that formed under conditions we do not yet understand. There is a competing view, and it deserves a fair hearing. Many physicists believe that neutron matter is stable all the way down. In their picture, no matter how great the pressure, the neutrons hold together and quark cores never form. The interior would be strange, yes, but built entirely from neutrons and their exotic arrangements. Both views fit the data we have. Both remain possible. The question of which is right may take another generation of instruments to settle. Future observatories may help. Gravitational wave detectors could listen to the vibrations of a neutron star as it settles after a merger. Those vibrations depend on what the star is made of. Deep down, a quark core would ring at a slightly different pitch than a purely neutron interior. If we listen carefully enough, over many events, a pattern might emerge. X-ray telescopes could measure the exact size of neutron stars with new precision, and even small differences in radius would hint at what lies inside. None of this will happen quickly. The mergers we need are rare. The signals we need are faint. It may take a century of patient listening before we can say with confidence what a magnetar's core is truly made of. And by then, the magnetars we study tonight will have aged, cooled, and quieted, indifferent to our curiosity. There is something soothing in that thought. The mystery does not need us to solve it. The stars will keep their secrets, whether we listen or not. Somewhere, right now, a magnetar is turning slowly in the dark, its core holding an answer we cannot yet reach. Maybe it is quark matter, maybe it is something stranger. Maybe it is only neutrons, arranged in ways we have not yet named. The universe is patient. It has all the time it needs, and so tonight do we. step back with me now, as far back as the mind can go. Picture the whole of the visible universe, that vast, slow-turning field of galaxies, each one holding hundreds of billions of stars. Somewhere inside that softly glowing web, scattered like rare seeds, sit the Magnetars. There may be only a few dozen of them, shining at any given moment across our entire galaxy, compared to the numberless stars around them. They are almost nothing, yet the fields they carry may be the strongest structures in the known cosmos. And here is the quiet thought worth resting on tonight. These small, fierce objects are made of the same stuff we are made of. Their neutrons were once protons and electrons in an ordinary star. That ordinary star was once a cloud of hydrogen and helium left behind by an older generation, and the atoms in our own bodies followed the same long road. The iron in your blood was forged in the heart of a dying star. The calcium in your bones was scattered by a supernova long before the Earth existed. The oxygen you breathe was cooked inside a star that never knew it would one day feed a listener drifting off to sleep. Magnetars are the strangest cousins in that family. They took the same raw material and pressed it into something so dense that our physics begins to stammer. When we look at them, we may be looking at a mirror held up to the deepest rules of nature. Every question they raise about matter, about magnetism, about the shape of empty space itself, is also a question about the ground we stand on. The same laws hold everywhere. That is the quiet promise of physics. Some researchers wonder whether Magnetars are teaching us that the vacuum of space is not really empty at all. Under fields, that strong, the vacuum may behave like a strange kind of crystal, bending light in ways no laboratory has ever seen. There are hints of this effect in careful measurements, but the evidence is still thin, and other explanations remain possible. If the effect is real, then space itself has hidden textures that only extreme conditions reveal. If it is not, then our understanding of the vacuum must still be missing something. Either answer would change the story we tell about the universe. Others wonder whether the interiors of Magnetars hide states of matter that exist nowhere else. Perhaps a soup of free quarks, perhaps a stranger substance we have not yet named. We cannot open one up to see. We can only listen for tiny tremors in their signals and try to guess what shape of heart could beat that way. The guesses compete, none have won. And that ongoing argument, gentle and patient, is one of the most beautiful conversations in modern science. There is a humbling thought in all of this. The atoms that make up your hand were once free protons in the young universe. They fell into stars. They were fused and broken, and fused again. Some of them may have passed close to objects like Magnetars during their long travels. The path from the first light after the Big Bang to the pillow beneath your head runs through places we barely understand. Every breath you take is a small conclusion of a story that began nearly 14 billion years ago. Magnetars remind us that the universe is not finished revealing itself. For every mystery we resolve, two more open behind it. The 2004 flare that touched our atmosphere from 50,000 light years away was a whisper from one of these objects, and we are still not sure exactly what it was trying to say. Somewhere out there, right now, another Magnetar may be trembling, gathering strain in its crust, preparing a signal that will not reach us for centuries. The sky is patient. It sends its letters slowly. You do not need to solve any of this tonight. No one does. The people who study these objects also go home at the end of the day, sit with a cup of something warm, and let the questions rest. That is part of the work. Sitting with the unknown is not a failure of thinking. It is thinking at its most open and most honest. The universe is under no obligation to be simple, and we are under no obligation to understand it all at once. So let the picture widen one more time. Galaxies, stars, a few rare Magnetars glowing in their fierce silence. And here, on a small blue world, one listener slowing their breath, made of the same ancient atoms, wandering along with everyone who has ever looked up. That shared wandering is old. It is older than any answer, and it is enough. And so we come to the quiet edge of the night, where the questions we have gathered can rest beside us like small warm stones. We have wandered a long way together. We have stood at the crust of a Magnetar, listened for the slow tick of a pulsar, and watched, in the mind's eye, two neutron stars fold into one another and scatter gold across the dark. None of it has been solved. That is the gift of this kind of listening. The universe has handed us a set of unopened letters, and tonight we have simply held them, turned them in our hands, and set them down again. Somewhere, right now, a Magnetar is spinning. It is small enough to sit inside a quiet bay, yet heavy enough to reshape the space around it. Its magnetic field is doing something no laboratory on Earth can copy. We do not know exactly how it formed. We do not know what its inner layers are made of. We do not know if a stranger form of matter waits beneath its iron skin. And the beautiful thing is that we do not need to know tonight. Picture, if you like, a small blue world turning slowly in the light of an ordinary star. Its oceans are calm. A soft wind moves across the water. Somewhere on that world, a person is lying in a warm room, the way you are lying now, letting their thoughts drift outward. Above them, the sky is scattered with light from stars that finished their long lives before humans ever looked up. Some of those points of light are the ashes of supernovae. Some are the slow glow of pulsars, sweeping their beams across the void. Some may be Magnetars we have not yet found, quietly holding fields we cannot yet explain. The galaxy itself is turning too. It turns so slowly that no eye could ever see it move, but move it does, carrying every star and every stellar corpse in a great patient wheel. Our sun rides along with it. So does every neutron star we have talked about tonight. They are all part of the same slow current, the same soft turning, the same quiet music that has been playing for billions of years without anyone needing to hear it. There is something gentle in that thought. The universe does not require an audience. The Magnetars flare whether we watch or not. The pulsars send out their beams whether or not any telescope catches them. The great clouds of gold from ancient collisions drift onward, mixing into new worlds whether we ever learn their full story. And yet, here we are, small warm creatures on a small warm world, listening in, wondering, letting the mystery in. Let your breathing slow now, if it has not already. Let your shoulders rest into whatever holds them. The questions we open tonight will still be here tomorrow. The Magnetar's field, the Quark core, the fast radio bursts from unknown homes, the trembling crust, the silent partners in silent orbits. None of them are going anywhere. They are patient. They have been patient for a very long time. You do not need to solve anything before you sleep. You do not need to picture the whole galaxy. You only need to know that somewhere out there in the deep dark, a small dense star is spinning, and its light is old, and its field is strange, and its interior is a puzzle no one on Earth has yet cracked. That puzzle is not a burden. It is a kind of company. It waits, glowing softly while you rest. Imagine, one last time, a still ocean under a pale moon. The water barely moves. The sky above is thick with stars, and each of those stars has its own story, its own end, its own quiet secret. Some will die gently, Some will collapse and leave behind the small, strange objects we have spent this long night wondering about. And all of it, is held in a universe that does not rush, does not shout, does not ask anything of you tonight. We may learn more in our lifetimes, we may not. The Magnetars may keep their secrets for another 100 years, or another 1,000. For now, it is enough to have wandered. It is enough to have stood, in imagination, at the edge of something we do not yet understand, and to have found it beautiful rather than frightening. Sleep well, the mystery will keep. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.